Right जी, welcome to the 16th lecture. So last time क्या discuss किया हमने याद है किसी को?
This random walk Markov processes की types में discuss किए थे तो the random walks जो spend किया था
So where did we start?
from Markov chain.
Markov process, Markov chain, yeah. So क्या चीज़ थी? What was the magical thing that starts this field? What assumption or say condition or test or a question whose answer describes if this is a Markov process or not? क्या था? Moving
Markov problem.
Markovian property. Yeah. What was that? So let's say if a there is a sequence, let's say xt. Yes. What was the requirement that it has a set of discrete set of states? Let's say we started with that. Yeah. But in general, let's say there is a sequence xt. Yes. So what was the Markovian property on this that started the Markov chain thing? What makes it a Markovian process? एक वो requirement थी, yes? If probability क्या था?
Preceding probability
Yeah, xt
given where
xt 1 xt minus 2 xt minus 3
same
and
as
so on
is
was
same
the same as
preceding
probability. Yes. So it started with a conditional probability question. Yeah, it is that the from a statistical point of view or from the point of view of assigning probabilities, the information contained on the whole history is the same as the information contained in the preceding value. Yes, if that is contained in just one preceding value, this was first order Markov process. Yeah, if it was contained in two preceding, then it was second order Markov. But this idea, this question that can the whole history be reflected in the recent values, right, depending on the order, is what sets the Markov field. Yeah, the Markov, the field of Markov studies. Yeah. So these are Markov, then this becomes a Markov process, and we started with the discrete time Markov chain, if you remember. Yeah, so we described some of those, but then we went on to define something called a random walk. Yeah, उसमें क्या था? What was the random walk? How was it related to Markov processes? We showed that the random walk was in fact a first order Markov chain because it satisfied this thing. Yeah, what was there? We had this Sn, if you remember, it was Sn minus 1 plus Xn, where Xn was a two-state process. It could be plus 1 or minus 1 with probability p and 1 minus p, and there was an additional assumption that all the x's x1 x2 were independent of each other. With that setup, we got something that was a random walk, right? So it was a value that starts somewhere at t equals 1 2 3. At each of these fixed points, it will either go up one step or go down one step, and that thing was, and whether it goes up or down was probability p or 1 minus p. That's one thing. Second, the decision that it took here was completely independent of the decision that it's going to take on the next step. In each step, the decision it takes to either go up or go down is independent of the previous. That's what it means to have these independent, right? So like this, and then maybe it comes here. It could go to negative, it's fine. Yeah, so again, this is something that led to the random walk. Yeah, So random walk, it could keep going on up for a while, then go down again. This was a random walk, and this was a first order discrete time Markov chain, yeah, or process. So from the Markovian property, from Markov we went to random walk. It was a special case, yes. Then where did we go? Where did we walk off to from there? Brownian motion, yes. How did that come from here? Brownian motion was a
special case of this.
special, in what sense? Or was a limiting case of this thing. Yes? He said that if this jump approaches 0, this delta, and let's say this is delta h or something, so if this h approaches 0, right, then how did the process look? Then we said it can be, right, transitions can be big, can be very small, it's approaching 0, and they can occur almost continuously, yeah. So this was a limiting case, limit delta delta goes to 0, h goes to 0, and then there was some condition that delta over h square had to be constant, yeah, to avoid degeneration. Other than that, it's basically the so random walk is an instant of Markov processes, and then so from random walk, if we put a limiting case, that became the Brownian motion, right? And this one discrete time Markov chain of first order. So Markov chains, within that discrete time Markov chain of first order, one was random walk, then the limiting case was Brownian motion, yeah. And then what did we say about did we generalize that further, or there was one more thing that we discussed? Kya tha? Of course, we also discussed if any of these are stationary or not, or those things. But other than that, I'm just giving the overall view. The fusion processes, right? So, diffusion processes. This Brownian motion was then a special case of diffusion processes, okay, which are in fact continuous time Markov chains. So discrete time Markov chains to continuous time Markov chains.
It is compulsory condition that the value of the x, that value will take, it will be discrete.
X
discrete state कह रहे हैं ना हम इसे.
For this x.
No,
Yeah.
for Markov processes, Markov process में सारे आ रहे हैं, तो इसका मतलब Brownian में सब में हमारे पास x value लेगा वो discrete ही होगी.
For discrete time Markov chains, that will have to.
Discrete state हमने कहा है ना जैसे.
Sorry, discrete state. Yeah, for discrete state, it will have to be discrete. Random walk is not the only Markov discrete time Markov chain, right? There can be more. In this is one instance of that. Yeah. And if you are talking about any discrete time, discrete state Markov chain, any that can be other than random walk, then by its definition, if you're calling it a discrete state Markov chain, then it should have a discrete set of states. Otherwise, it will be a continuous state. I think I wrote it like this: continuous state Markov chain. Yeah. So don't think of it like that the random walk is the only discrete state Markov chain. There are others. Yeah. Then by definition, if you say, okay, I have a process which is a discrete state Markov chain, that could be random walk or some other process. If you're saying by yourself that it's a discrete state Markov chain, then you've already established that it has discrete states. But Markov itself is not limited to discrete states, right? It can have continuous states as well. Yeah. So it's a broader class. Okay, so for example here, yeah, maybe we'll come back to that later. Let's see. But this, in this case, this is, if we want to write even further, we could write continuous state, continuous time. Yeah. Whereas this was, if I recall, yeah, this was discrete state, discrete time. Yes. So, and this is continuous state, continuous time Markov chain. Yeah. So यहाँ पे you are discrete on both the end. If you remember when we started random processes, we discussed examples of all four options. Yeah. So again, the requirement of discrete or this or that is something not really say a full requirement for Markov chains, which is more general. So it can cover both of them.
The main requirement is that you can just predict from the preceding one.
Yeah.
That is the main.
Yeah. Yes. Whatever that was. Okay. So this is a quick review just to recap. Main concept, of course, we took a whole lecture to do that. So please review that. Today we move on to something a bit different. Or let's say looks like a bit different class of random processes. I mentioned that last time. You know the Poisson process, you've heard of it, yes? And the class we're going into now is, it covers the Poisson process. In fact, Poisson is probably the most popular process in that class. Yeah, and that is the class of point and counting processes. Okay, so you have come across counting processes, देखें किसी course में या before this, yeah. So in a lot of studies or works that we do, what you want to do is find the happenings of events. How many events are happening? Let's say if you are a shop, you want to see how many customers arrive in next hour, right? If you are a government, you are interested in, okay, how does the population, what is the death rate and what is the birth rate, so you can calculate the net population expected over next month, next 3 months, and so on. Yeah. So there is a long, in queuing theory also, it's a long list of problems, applications. You could study it theoretically or link it to real problems of queues, where you want to see events happening, yes, and you want to then talk about their statistics. Like for example, what are the chances that in the next 10 seconds 15 of these events happen, right? And these things also show up in your radioactive nuclear studies and all those. Yeah. So what is the probability that the next 3 events will happen within this time? That's the question in a different way, right? Then what are the, how are the spacings between the events, how are they distributed? Can we predict something? This spacing is less likely, this spacing is more likely. So all of those, as you can generate so many questions from this, and all those questions, depending on your application, will help you design something or answer some important parameters. Yeah. So Let's start with we have this continuous time discrete state process. Let's consider that. The other continuous time. So we are looking. Let's consider a continuous time discrete state. This is very interesting. So it is continuous in time, yes, but the states it can take are fixed. Yeah. So that's one thing. Okay. Second, in this process there are point events occurring. Okay. So that's what gives the name point.
It will always be
Yeah.
continuous time discrete state process. Poisson.
No, for Poisson I am talking about this general one. We're starting with the general point and counting processes, right? So, and in this process, let's say there are point events occurring. That's where the name comes from, yeah? Point events occurring. Point event means the arrival of a customer, departure of a customer, yes, decay of a radioactive nucleus, so call coming in to a customer center, all that. Clicks happening to a website, events, yeah. So point events occur at different times, yeah, and they occur randomly at times, let's say t1, t2, tn, and we keep a count of the cumulative events. So that's where the word count comes from. So point events occur randomly. We will make this more precise later, but they're not deterministic. Okay, so they occur randomly. क्या जो आते हैं कस्टमर आते हैं वो डिटर्मिनिस्टिक तो नहीं आते ना, राइट? क्या कहते हैं, मौत और गाग का कोई टाइम नहीं कुछ है, राइट? सो डेथ एंड कस्टमर कैन कम एनी टाइम. So occur randomly at t1, t2, tn. Okay, there is nothing saying that these are equally spaced. We don't know what they are. Right? We're just assuming we have indexed them from smallest to largest. This could be 1, this could be 10, the next could be 30, whatever. We're not saying what they are. They're just any t1, t2, just in this order, and they are random. So they follow some, they're not deterministic. Yeah, they don't follow a formula that they are linearly increasing, quadratically increasing, not a deterministic formula. They are randomly. So that means what? The events are occurring randomly. First customer comes in, yeah, at this time. Then second customer, is there any requirement that the second one should come 2 minutes after the first one? Hota hai, maybe not all day. Any customer coming in, yeah, and maybe it's a busy day. Every few seconds someone entering, new guy entering, new customer entering, yeah. So these are random, and now we keep a count of the cumulative events. What does that mean? So we count cumulative events. So we say that I am going to say that at any time t, I have a counter nt which counts the number of events in 0 to t. Okay, in this time whatever events occurred, I keep a count of this. So that's where the whole name point and counting processes comes in. Okay, so there are point events, we keep a count of their cumulative or their sum, and that is, so if this is n, let's say we're talking in seconds, yeah, so if this is n20, what does it represent?
For 20 minutes, how much customers comes in?
Yeah, so let's say minutes, okay. So that means from whenever you started counting, from there on, that will be a 0. From there to up to
20.
a time of 20 minutes, how many customers came, if it is a, or how many events occurred, whatever they are. Yes? This is the count we are keeping. Okay. Now it's quite interesting that there are now not one but two random things going on here. Yeah. What are those? So and t itself is random. Yes. But the t's are also random. Yeah. So actually, depending on what we look at, we will see that there are special cases coming in. Okay. So first, let me plot this or draw this to make it clear. So let's see how does this continuous time discrete state process that we call point and counting processes, how would it look in this case? So firstly, nt, is it discrete state? Now I'm talking about nt. Yeah. Well, t's are not the point and counting process. nt is the point or counting process. Okay, two names actually being used. So I'm saying both. So we are talking about nt. Firstly, does nt satisfies the discrete state characterization or not?
Yeah.
It does.
Yeah,
Yes. So
number of customers
the way we said events are point events, so they are occurring, right? So they will add or let's say subtract some values. So remember, nt is keeping count of the events. ये नहीं कि वो कितना आया था यार, right? So it's more, it's just a count. So that way, let's say it starts at 0. So let's say no customer had come. दुकान खोली आपने नई नई 0 पे, yeah, no customer has come in and the first one shows up at t1. You don't know what t1 is, yes, but from 0 to t1, what is the value of nt?
0, no customer.
0. Yes, but is nt, it is discrete state, we know, yeah, but is it also continuous time? It is, because you can calculate nt here, anywhere you like, right? Can be, and it's continuous time, but discrete in state, because you're just counting the events. That's it. So at t1, first event occurs, maybe a customer comes, and your counter goes to 1. Yeah. Now then after t1, let's say, when does the next customer come? At some t2, maybe very late after this one here. Now from t1 to t2, you are stuck here. Yeah. It may look like this has two values here at t1. To avoid that, we often write this one as a, so the opening of the interval is open, but the closing is precise. Yeah. So often we write it like this to make that clear. Right. Now up to t2, can we find nt? Is it continuous or not? It is continuous, yes. And nt continuous in time, I mean. Yeah.
Yes, sir.
So what is the value of nt here?
1.
Depends, yeah.
Yes, sir, depends.
From 0 to t1 it is 0. And then from t1 to t2, yeah, it is 1. Yeah. So if you pick a t here, you get a value 1. If you pick a t here, you get a value 0. If you pick t1 exactly, you get 0 also. Yeah, because of this square bracket.
सर n of t जो हमारे पास वैल्यूज आएंगी उसकी वो हमारे पास डिस्क्रीट होंगे नीचे 1 2 3. देन आप कंटिन्यूस को किस तरह करना, मतलब t1 से t2 हम t1 t2 ये हमारे पास पॉइंट्स हैं, ये इटसेल्फ हमारे पास जो है वो डिस्क्रीट तो है, लेकिन अगर हम इसे देखा जाए कि इस एक्सटेंशन में तो हमारे पास कंटिन्यूस है. n of t को सर हम किस तरीके से मतलब कह रहे हैं कि हमारे पास कंटिन्यूस है? आप इस सेंस में कहते हैं
continuous time, yes, because you can calculate or talk about this process at any time. Let's say आप कहते हैं, let's say this is you want to know कि जी पहले 30 minutes में in the first 30 minutes how many events have occurred. Yeah, so you can try to calculate n30. Nobody is stopping you, right? Does the next event have to happen at at 30 minutes? No. Yeah, event may have happened anytime, but you are not barred from trying to talk about the number of events at any given time t. Since you are allowed to put any continuous value here, and t is continuous in time, है या नहीं? उसमें change discretely आता है, ठीक है? Yeah, but the process itself, the t here, is it in R or not? Simple say है ना? हमने तो restrict नहीं किया कि जब whenever there is an event only then you can ask this question. You can start by saying, even without starting the process, you can, okay, how many events will occur in 35 minutes? So you have set a time here, 35. Yeah. Now how that changes and gets to, now let's say for 30 minutes, maybe 2 more events have happened by then. Yeah. So let's say there's an event happening, so it goes up and stays here, then it goes up and stays here, goes up, and next event may be happening here, but you asked for 30 minutes, so you can get your answer. Yes, what is the count at this time? So because you are allowed to pick any t, and there's a reason for that, because often you don't want to say, okay, I will only look at my process when there is an event happening. You could look at it in between. पहले से आप set कर लेंगे जी, what's the chances that so many nuclei will decay in 1 hour, right? So ये इस तरह की चीजें, all of that is covered. But yeah, state of NT. So this is NT, yeah. The state of NT is discrete, you're counting, yeah. But the t variable is continuous, even though the events themselves, of course, are still discrete. The t1, the special ones. But in between, t has a value, and you're allowed. इसलिए हम इसको ऐसे draw कर रहे हैं, yeah. So it remains constant, yes, but it has a value there, yeah. So it is a valid value. Let's say this is saying number of events in the first 30 minutes, yeah. So yeah, the value is constant, but it's a valid value. How many events happened? 1, 2, 3, 4, yeah. And maybe the answer to number of events in 35 minutes is also the same. It's fine, but I mean it is a valid value there, yeah. Okay, so this is a let's say drawing of this thing. We are interested in point events. As I said, we call them the point processes, and we just set this up, yeah. Now we go to the next stage, which is what we call a special case of the point processes. Okay, so to get a point process or a counting process, this is only condition, nothing else. Everything, any process that satisfies this thing would be a point or counting process, yeah. Now let's start putting conditions on it to make it more interesting. So the first condition we could put on it or talk about is the spacing between occurrence of events in this thing, yeah. So previously I said these are happening randomly, yeah. If they're not happening randomly, deterministically, this is not a random process then. So first, that is a requirement to have a point or counting process. But then let's say we want to talk about the spacing between two events or two occurrences. So what does the spacing look like? Let's say this is the spacing between these two events, yeah. Because the events are occurring randomly, you don't expect the spaces to be same, yeah. They are also, now the spaces are random variables, yeah. So let's define the space. Let's give it a name. So we will call xn, we'll define it as the time space between two adjacent times of events. So x1 basically, or you could start with 0 if you want to set that to t0. x2 will be t2 minus t1. Yeah. So x3 will be the spacing between
T3.
this is t3. Yeah. So then this will be, this is x2, this is x3. You could start with x1 with this set to 0. So x1, x2, x3, x4, and then if the next event occurs here, then this. So you see, these spacings are, you can imagine they are random. Yeah. So the spacings are random variables, but that is by definition of the point and counting process. But now this is one interesting condition that we are going to put on it, that will give us a subclass of the point processes. Okay, that is called renewal processes. So what is that? The condition we are going to put on it is this: if xn are IID. याद है ये? We discussed this 2 lectures ago when we discussed moving average. Independent, identically distributed. Yes. So in that case, what distribution did we put on xn? We didn't define it. Yeah, uniform, Gaussian. We didn't set that yet. All we said is that all these spacings have to be independent of each other, and whatever distribution they are coming from is the same. They are all coming from the same distribution. Okay, Gaussian है, Gaussian है ना वो है, exponential है तो exponential है, whatever that is, it is the same. If this condition is met, then we say that the process NT is a renewal process. Okay, so what happened here now? You had this point or counting processes. They didn't put any condition on these spacings being independent or identically distributed. The only thing it said was that the instances have to be random. If they're not random, you are talking about deterministic process. So that's the only requirement. It was very relaxed. Yeah. Then we put one condition on it, that with all that, an additional constraint is that the spacings between these random happenings have to be IID. Yes, this is a realistic assumption actually. That's why people got it. So then you come to renewal process. Yeah, NT, which is a point process already, now it becomes a renewal process. Okay, right. Now we are going to put one more condition on it. Okay, and we will get to our target, which is the Poisson process. Okay, so another condition that we want to put on it is this. Here notice we said xn are IID. We didn't say what is the distribution. Yeah, let's say in addition, this was first condition that made the further subclass renewal. Now if we put another condition that xn are, any guess?
Poisson.
No. Poisson process में जो time instance है उनकी distribution क्या होती है?
N lambda I guess something this होती है, something alpha is equals to n t.
Yeah, you're calculating the mean I think, but yeah, basically xn are exponentially distributed. Okay, so what's happening now? There is now an addition condition. Firstly, if they were IID, this was the class of renewal process. Any process that satisfies this and is a point process becomes renewal process. Then if this identical distribution happens to be exponential distribution, then this thing becomes Poisson process. Okay, I'm not talking about Poisson distribution. Yeah, Poisson process. And now we will see why is it called Poisson process, because the distribution is exponential. Yeah, any guess?
The exponentially the distribution be distributed xn, तो ये फिर identical किस तरह होंगे सर? Identical तो मतलब same हमारे पास नहीं.
Identical distribution means they come from the same distribution. Let's say one of them was exponential, the other was Gaussian. Then they are not identically distributed. ये होता है identical distribution. Okay, that they come from the same distribution, or actually we require them also कि उनके parameter भी same हो. So if there, let's say x1 comes from Gaussian with mean 0 and variance 1, and x2 comes from Gaussian but mean 2 and variance 10, again they are not identically distributed. Identical distribution requires that their PDFs are exactly the same, which means their CDFs are also. ये होता है, alright? So they are exponentially distributed. That means all of them are exponentially. That's what makes them ID. Yeah, I didn't mention here that with the same parameters because we have already discussed this. ID. Independence is something separate. Independence का आपने concept already पढ़ा हुआ. So they have to be independent. They have to be identically distributed, and that distribution, if it's Gaussian, not Poisson process. If it is uniform, not Gaussian process. Not Poisson. Only when this identical distribution is the exponential distribution, then we can call NT a. NT is now a Poisson process. Yes. So, any thoughts? Why give it? There is a Poisson distribution भी होती है ना एक, yeah. So why give it the name Poisson process, not exponential process? मतलब distribution तो ये वाली है. So it's very simple actually. So let's write that here quickly. It can be proven. I'm not gonna show it here, but it can be proven that whenever xn are IID and xn are from exponential distribution, if you start with these two assumptions and then calculate the probability distribution of NT, you know what it comes out? Poisson distribution. NT will have a Poisson. It's a necessary conclusion. I'm not proving it here, but it's a necessary conclusion. Whenever you have this setup and the spacings are IID with each one following the exponential, then the necessary result is that NT will follow Poisson distribution. So that's why we call it a Poisson, because remember the process is this one, not this one. Yeah, it was spacing one. So process is here. So NT will follow Poisson distribution, and that's why we will call it. We will come back to this Poisson. There is a whole chapter in your book on Poisson process. So we will come back to Poisson and Gaussian processes later. Right now I'm just giving you the big classes, yeah, where they fit in. Yeah, then we will come to this. So in fact we can also go on add this, that Poisson is a continuous time Markov chain. Okay, so the Poisson process is itself a continuous time Markov chain. Um, Basically, any continuous time Markov chain requires the spacings to be exponentially distributed. If the spacings are not exponentially distributed, then a continuous time process does not satisfy the Markovian property. Okay, and then we call it a semi-Markov process. इसमें जो उसकी मेमोरी लेस प्रॉपर्टी है वो सेटिस्फाइड नहीं हो रही।
मार्को भी नहीं कहेंगे, पर्सन नहीं कहेंगे सर।
No, this is additional thing. What we are saying is that the Poisson process is a continuous time Markov chain. Okay, and the reason that it is because any continuous time Markov chain must have these things to be exponentially distributed. Okay, so again I'm not proving it up. You can find in I think in Kobayashi, or if you search for it you'll find the proofs. थोड़े से extended होते हैं, but the concept is this thing. Right, so last page, I'll just close this with one thing that adds on top of these things. So the next one is not a subclass of this, but it's related. Yeah, I mentioned population. Now, could you model populations with what I've already mentioned here? Not really, because it seems to be counting one thing, either deaths or births. Population can have both.
Both, yes.
Yes. इसी तरह if you are studying flow of some material, if the flow can be two-way, some say molecules going one way, the other molecules, or some molecules coming in, the others going back, then flows and all these things can be both ways. Counters can be up or down. All the things I have discussed so far are just counting up, right? So these processes that we have studied, often they are called pure birth or arrival processes, and by necessity they are non-decreasing. These, yeah, are an idea. Count ही करना ना. We didn't allow you to count down कि कोई चला गया, right? Event को वापस लेने का हमने कोई discuss नहीं किया. But you can imagine in population, in many situation where is arrival and departure, and you want to see, okay, ये डेवो का स्टेशन है, at any given time इसमें कितने लोग होंगे. Is it enough to count के कितने आए थे अंदर? To answer this question, no, right? You also need a statistics on how they are leaving. So you are dealing with 2 point events, right? One point event is arrivals, the other is departure. In population, it's one point event is births, the other is deaths. Yeah. So these processes are sometimes called, you will see in the books, they are called either pure birth or arrival processes also. ये जो point processes, yes, जो counting processes सारे, उसके अंदर Poisson फिर है तो वो उसको apply होता है. But then there are processes that we call birth-death processes. I won't go into details of those. We need full courses on covering इतने सारे, वो उसके लिए और कोर्स किया जाता है. लेकिन birth-death processes. The reason I emphasized on the birth thing is because this new set of processes is इसका नाम ही है, yeah. So basically, so you don't get confused. By this they mean that you're counting up and down, yeah. So in birth-death processes, you are interested in arrival and departure and so on. So let's say this is something, and at random time intervals you could count up or count down. Okay, so the example here, one event occurs as a plus event, and then at t2 it's another arrival, let's say, and then, or a birth, and then at t3 maybe there is a death or a departure, we come down one step, and then maybe nothing happens for a long time, then another birth, then maybe death, and so on. Yeah, this NT is called the birth-death process.
We're counting all the sir births of the previous one also, or was for a specific interval we are taking it. Let's say from T2 to T3 there are 6 births, and from T1 to T2 there are 2 births. So sir T1 से T3 जब हम लेंगे तो सिर्फ 6 को देखेंगे या पीछे वाले तमाम births को देखेंगे? Is it a cumulative thing or something?
Up to NT, it is a cumulative birth minus death, right? So अगर आप यहाँ पे देख रहे हैं इस point पे, what happened here? We're calculating the net. Yes, what is the net? So is it how many births and how many deaths overall?
Okay.
Cumulative है ना, इसका net है ये net. So it's plus and minus. Yeah, it's already done here. So one arrival, 2 arrivals, then 1 departure. So 2 minus 1, and this time there is just one person in this room or this population or whatever. Yeah. So then we can write NT as a birth minus death process, birth and death. This is now interesting because each of these is now that guy. Yes?
Not sir death minus birth process.
You could define it like that or also, it's fine. It will depend on what you want to call birth and what you want to call. It's not a real birth or death. Yeah. Your problem will define what is the first one and what is the second one, right? So this is the, what is this? Count of events. Count of events in 0 to arrivals in 0 to T. Yeah, and this is count of departures, deaths, whatever the opposite you want to have in time 0 to T. Yeah, so each of these is a counting process. So essentially their difference, if it's written this way, is the birth-death process. So that's how it is related, but it's not really a subset of this. It's built on 2 point processes, right? So 1 point process counts up, the other one also counts up in the sense that it counts the deaths, ek death, do death, teen death. But if you subtract one of them from the other, that's when it becomes a birth-death process. Okay, and again they are heavily used in statistical studies of population, of decays of atoms, all that concentration changes in chemicals. So with this we have covered our broad topics, yeah, of random process examples. Yeah. We will come back to go into details of the Poisson and the Gaussian. We haven't defined the Gaussian process yet. Yeah, वो I've saved it for Gaussian distribution आपको पता है, but how do you define a Gaussian process? वो later it will come. But overall we have covered this. So we started with what? Random harmonic with amplitude changes, then moving average, then random harmonic with also phase random, additional randomness. So this was 3.
Markov.
Then we went to the whole what we covered in the start, the Markov thing, link that to random walk, link that to Brownian motion, which is another name for Wiener process. Then we link that to diffusion processes as being a subclass. Some things we just touched upon to give you an idea of where we stand. Yeah, each one को हम उतनी detail में नहीं कर सकते, right? So from there we went into a mostly a different domain. Yeah, इस domain में वो जो Markov idea या जो harmonics, that's not here, right? This is something very different. This is the group of mostly point and counting processes and their relative, the birth death process. Within this we saw, so you have the general point and counting process. Within that, if the spacings are IID, they become renewal processes. If the IID, the ID part is actually exponential, then you have a Poisson process, because then NT follows the Poisson distribution, right? So this is a very quick summary of what we have done. Next time I think we will talk a bit about estimation. Okay, so आपको आइडिया है estimation का? Estimate लगाते हैं कितने में मान आएंगे, देख कितनी बड़ी बनानी, right? Estimation, yeah. So what we will see is that if you remember, we said that the working with distributions is hard, so we take their proxy, surrogate the mean and variance. It turns out that in real cases, you don't really have nice distributions from which you can derive this mean. You normally have to estimate the mean and variance from collected data. Yeah. And as soon as you start estimating, the estimate itself becomes random. उसके अंदर कुछ error होता है. So we went from random to deterministic, and now we will go back to random. Yeah. So we said X is random, very hard to work with. We are going to work with mu X, sigma X, yeah, or the covariance of X and Y, for example. We work with these. We said that, yeah, because this is uncertain world, so we will go to the PDF plus the moments. But now we realize, hang on, in real world you don't really have nice distributions here, so you have to estimate these guys, meaning after we put a hat here, you have to estimate them from whatever data you have. But when you estimate, there is a chance that there will be some error. Yeah, if there is an error, so this was deterministic, but now you're back to random. This was random, deterministic, and back to random. So फिर क्यों करेंगे हम ऐसा? Yeah, the thing is, this will be less random than the original. Okay, so we will try to estimate these variables, these moments, based on, or we'll try to talk about how can we estimate based on random data, such that the randomness here remains low, the mean and the variance of this process of these estimates is low. So let's say the true is here, then you will have plus minus delta mu X, which will be your estimator in most cases. Yeah.
Yes, sir.
So what do you want this guy to be? Basically 0.
0.
Yes, but in fact it will turn out to be a random process itself, and in many cases it will be Gaussian distributed, and if your estimator is good, then it will be centered on mu X, its mean will be the true mean, and its variance will be very small if you're estimating.
Yes, sir.
That's where we'll come with the idea of what is a good estimator.
Biased and unbiased.
Yeah, and consistent or not,
Yes.
all that. Yeah, so it's a very important part of stochastic processes, because you have to work with estimators. So that is the next module, and after that we will come to Poisson and Gaussian process. Yeah, okay.